Welcome everyone to the last speaker night of 2023 in Mississauga Center. Where'd the time go? What I think we will do is we'll have some announcements after the talk, and given the fact that our speaker is remote, we probably will go right from the talk to Q&A, and then after that, you know, if there's is there a raffle tonight? Yeah. So don't rush off afterwards, buy tickets. And the whole idea of coming to the meeting is just to chat. So, but the thing is, we won't have a break with the speaker. So it'll be a little bit different. Okay. Well, so my name's Randy Atwood. I'm the president, and I'm very pleased to be able to introduce our speaker tonight, Dr. Matthew Svensson from Western University. And hopefully you've had a chance to read the synopsis of his talk. Very timely, given the announcement in Montreal earlier this week about some astronaut missions being announced. Dr. Svensson is a planetary scientist, and it's a great time to be a planetary scientist, actually, given the fact that there are a lot of spacecraft out there whizzing around the solar system and on the surface of Mars. So it's interesting how so many Apollo astronauts came up to Canada, specifically Sudbury, to practice before they went to the moon. So Canada must be very, very moon-like because of the interest that people have in studying our rocks and our geology. Dr. Svensson tonight is going to talk about the Artemis program and the recent expedition to Kamistatin Lake in Labrador. And it's interesting how he'll tell you on the team, there were 2 people who are on the upcoming Artemis mission and 1 backup astronaut. So with that, please welcome our speaker, Dr. Matthew Svensson.
All right, thank you very, very much for the introduction. My name is, as I said, Matthew Svensson, and I'm a postdoctoral associate. Actually, can I just make sure everybody can hear me? We're good on that end?
Yep.
Great, fantastic. Okay, so I'm a postdoctoral associate at the University of Western Ontario in London. And firstly, I just wanted to say thank you very much for the invitation to speak here with RASC. It really is an honor to have the chance to speak for this organization that has such a long history and heritage in astronomy and planetary science. And today I'm really lucky to be presenting about the Artemis program, which for those of you who don't know, which I doubt is many of you in the room at the moment, is our most recent effort to send astronauts to the moon and beyond since the 1970s, the Apollo era. And I'm going to be talking about the Artemis program kind of on a whole, and our most recent expedition to Kamistatin Lake in Labrador. As we said earlier, Canada has quite a bit of heritage in astronaut training, with the Apollo astronauts going to Sudbury. Now we have Artemis astronauts going to Labrador, another lunar-like site in Canada. Just a brief background about myself: I got my PhD just about a year and a bit ago, where I focused mostly on impact cratering, planetary science, astrobiology, and mineralogy, and that sort of thing, and kind of did a bunch of rover operations research in that time, and then ended up transitioning into doing developing training programs for astronauts with NASA, and ended up very fortuitously on this expedition where I actually was involved in contributing to the development of some of these training programs and helping take the necessary steps in preparing our astronauts for going to the moon in short order. So with that, I just wanted to start off by introducing the Artemis program and the science rationale for it. So shown here is a photo of the Orion capsule taken during Artemis 1, which flew in 2022. But I mainly wanted to show this photo because I think it really puts in perspective how big this endeavor is. Right? In this image, the Orion spacecraft, which is obviously the big crew capsule that I've labeled there, has traveled just beyond the moon, which, as we all know, is our nearest neighbor in the solar system. And you can see just how small the Earth already looks. And more or less the entirety of human history took place on the planetary bodies that are in this image. And Artemis represents a step that's even beyond that. Ultimately, the goal of Artemis is to extend the foothold of human exploration further into space and to eventually allow humans to walk on Mars one day. And there's, I think, a unique call to discovery for programs like Artemis that really seem to inherent international collaborations. And these missions have really become the crowning jewel of national achievement and a marker of our collective technological advancement as a species. And let me just advance my slide. There we go. So, like I said, Artemis, well, let me just back up a little bit. Artemis does not represent the first time we built a program with the intention of eventually sending people to Mars. So as a step towards that. Originally included in the goals of the Apollo program was to have astronauts walking on the Martian surface. It wasn't until we realized how incredibly massive this challenge was that the Apollo program was then de-scoped. So through exploring the moon as a stepping stone to Mars, Artemis is in essence a spiritual successor to the Apollo program. And in the background here, this photo that I'm showing is the last time astronauts went to the moon, which was Apollo 17 in 1972. And pictured here is Jack Schmitt, the first and only geologist to walk on the surface of the moon, for now, at least until I can trick someone into sending me there. And the advancement of sciences, specifically geology, is one of the biggest reasons why we're going to the moon. And so we're going to talk about that for a brief moment here. So why exactly are we going? And I'll address this GIF on the left here. It's a very discovery-driven process, and the big question is, how did the moon form? Our leading theory, looking at the animation on the left, is that a Mars-sized object impacted the Earth, and some of that material was ejected and condensed to form another rocky body, which was the moon, and that was then trapped by the Earth's gravitational pull. And we can hopefully learn more about this by going to the moon, sampling the rocks that are there, and then looking for geochemical signatures that can tell us about the moon's geological history. We're also interested in learning about the history of the solar system and how the solar system at large formed. We currently believe that there was a period called the Late Heavy Bombardment, a period where there were lots of small planetesimals in the early stages of the solar system's history that were colliding with each other, and there was overall just a much higher frequency of impact events happening on rocky bodies throughout the entire solar system. And this is what we have depicted on the left here. This is an artist's rendition of just impact events happening more frequently. And this is important for a number of reasons, but one that is interesting to me as somebody who was, it was and still is to an extent a bit of an astrobiologist, is that it can tell us a bit more about when life could have likely began to form. So, in theory, you're not likely to have life forming on a planet where the surface is exploding all the time. And so the idea is that this period in the solar system's history where there were collisions happening between these rocky bodies very frequently puts kind of an early limit on when life could have formed in the solar system. So it's good to go to the moon, understand the history of impact cratering, because the moon's surface is preserved and not recycled by things like plate tectonics and weathering and stuff like that we have on Earth. So you can see this really long, deep geologic history of the solar system recorded by impact craters on the moon. And so that's why the moon is important for learning about the impact history of the solar system and potentially how life, or when life could have began to start. Another major reason we want to return to the moon is for its resources. So you may recognize, you may not recognize it. This is a fairly unconventional way of viewing the moon, but these are two pictures of the south pole of the moon on the left and the north pole of the moon on the right. So the moon is tidally locked with the Earth, meaning only one side is always facing the Earth, as you all likely know, and the other side is always facing outwards into space. And at the poles of the moon where these craters are, there are shadowed areas that are permanently shadowed and never actually exposed to the sun. And so this is a recent new paradigm for how we look at the moon, as we think that there is likely water ice contained in these permanently shadowed regions where it gets very, very, very cold. And these are highlighted in the blue dots that are on these images. And so water ice is really important. It's the main resource that we're interested in when we're going to the moon. So of course you can use it to create drinking water. You can also break the bonds between hydrogen and oxygen to create rocket fuel. And the oxygen itself can also be used to create a breathable atmosphere. We're also interested in using the moon's regolith as a natural building material. So there have been several robotics concept ideas that have been put forward that essentially eat up the regolith like a Hungry Hippos game, and then spit out the regolith as like 3D printed blocks to essentially create these igloo-like structures to house human shelters and protect people from radiation on the lunar surface. Pre-existing infrastructure in the form of lava tubes, which are these really deep caves that already exist potentially on the moon, is another thing that we are interested in exploring and trying to understand how we can use this to shield human explorers from radiation while developing settlements on the lunar surface. So the Artemis program is our steps to getting to the moon and taking advantage of these resources and taking steps towards exploring what science there is to be explored. And so it's broken up into several stages, much like the Apollo program with Apollo 1, 2, 3, and 4. There's Artemis 1, 2, 3, and so on. And so we're broadly aimed at exploring the poles of the moon, and we have very big temperature fluctuations between minus 130 degrees Celsius in these permanently shadowed regions and plus 130 degrees Celsius in areas that get a lot of sun. And so we have these really hostile environments that we have also just never been to before, that we've never explored with rovers or with humans. And so returning to the moon has been broken into stages for this reason. Artemis 1 is the first step, which flew in 2022. With this mission, we mainly focus on testing the rocket that would be used for Artemis 2, which is going to fly next year. The Orion capsule, which is imaged here, actually did not have any life support systems on it at the time of Artemis 1. It was just focused on exploring the functionality of the rocket and then some of the functionality of the cameras that are mounted on the solar array and some of the thrusting systems that are on the capsule itself. So Artemis 2 is mostly focused on testing the Orion capsule as a life support system with a crewed flight. During this flight, we're focusing mainly on the human aspects, essentially testing living conditions, doing exercises, testing CO2 accumulation, etc. And this flight, I'm sure many of you know, in particular, has gained a lot of media attention, especially in Canada, because we can see here, this is the crew for Artemis 2, and on the right we have Jeremy Hansen, a Canadian astronaut that will be flying to the moon. He'll be the first Canadian ever to go to the moon, and as we mentioned earlier, his backup will be well, I don't think she was named, but Jenny Gibbons, another Canadian. So Artemis 2 is broken up into 15 stages. Its flight system, rather its flight journey. After the initial launch, with the rockets that are tested for Artemis 1, the boosters are going to be jettisoned and the main stage engine is separated. So it'll be much like the stereotypical image you see of a rocket launch where the boosters break off and the capsule is jettisoned into space. They do a couple of burns from the capsule to get into higher orbits. Then we hit stage 6, which is this kind of orange stage that's here, where we're going to demonstrate some of the spacecraft's capabilities that involve separating from what's known as the interim cryogenic propulsion stage, then rotating the spacecraft to face that cryogenic stage, then flying backwards towards it, and then departing again. So kind of doing these in-orbit acrobatics, testing these systems that were developed by the European Space Agency. Then there'll be a final burn, which is I can't quite see the number there. Right, stage 8, after which will be put into what's called a free return trajectory. And I think this is, to me, I think this is really quite cool, meaning they will return to Earth after the lunar flyby, even if they don't perform another burn from Orion's capsule. So they're going to be from stage 8, going to be going around the Earth and then around the moon in an orbit that prevents them from ever actually leaving our line of sight from Earth, and then returning to the Earth without actually having to do any maneuvers or additional burns. And so after Artemis 2 returns, the objective is to move forward with Artemis 3, where we have astronauts on the surface once again, doing the exploration work that we talked about earlier. So in order to do this, of course, preparation is quite paramount. As I said, this is a very hostile environment, so order to make the most of our time there, we really need to know what it is we're looking for and how to identify it and how to find it, grab it, and get out. So if we look at the lunar surface, we see that it is dominated by impact craters. And so understanding impact cratering is going to be very important for understanding how we explore the moon and how we take advantage of the resources that are there. And so the best way to explore impact craters is to look at the over 200 that exist on Earth, and we'll get into one in particular, as alluded to earlier, where we recently explored with some of the Artemis 2 astronauts and a couple of others. So it's important to first understand the impact cratering process. And so here we want to ask what is actually happening in an impact cratering event. Well, it's loosely divided into 3 stages. The first being the contact and compression stage, where the projectile immediately parts its kinetic energy into the target rock, generating these massive shock waves that propagate downward and outward from the point of impact. And these shock waves also propagate through the projectile as well, and create another type of wave called rarefaction waves, which causes complete vaporization of the projectile. And it's the complete vaporization of the projectile that marks the end of this first stage, this contact and compression stage. Then we move into the excavation stage. The complex interaction between the shock waves in the subsurface and the ground itself is actually what causes the displacement and excavation of this target material. So it's the shock waves that move the target material rather than the explosion and the impact event and the impactor itself. So excavated material is ballistically in place beyond the crater, and we get the formation of this big vapor plume, much like the clouds you see associated with volcanic eruptions and nuclear explosions. And this would include this plume would include a portion of the target material and all of the material that made up the projectile. But freezing this point, we can also see what is known as a transient cavity, which is kind of this bowl-shaped depression we've created here, and is kind of the typical geomorphological feature we associate with impact cratering, this kind of classical bowl-shaped. But when we get to bigger impact structures, we get more complex shapes. So as we can see, these are all lunar impact structures, by the way. On the left is a Linné crater, and it's our smallest one and the simplest one. So we actually call it a simple type of crater. So simple and complex craters are the 2 main classes of impact structures. And the bigger they get, the more complex they get. So at greater diameters, we get something called the central uplift, which is kind of this peak in the middle of this crater. And at even greater diameters, that peak collapses to form a ring, like we see here at Schrodinger, which is the biggest of these 3 at 312 kilometers in diameter. And in the aftermath of these impact events, we get these hot, melt-rich environments. For the sake of this being a lunar analog, let's just ignore the water table there, because that does not exist on the moon. But we are going to get these pools of what we call melt. So this molten rock that is then going to cool, crystallize, and create new types of rock. And any type of rock that is either modified or created by an impact event is called an impactite, which we'll come back to later. And so, as I mentioned, there are lots of impact structures on Earth, and we want to go to one that is as much like the moon as possible. And so we chose what we call Mistastin Lake in Labrador, which is called Kamastastin Lake by the Innu Nation. It's the First Nation community that whose land who this land belongs to. And so, why exactly do we want to go here? And the simple answer to that question is that the rock type that exists at Kamastastin Lake is the same rock type that makes the moon white. So the vast majority of the rock that is on the moon is this type of white rock called the northocite, which we see outcropping here by the riverbed. It's that this very bright white rock there. So we get up close to it here. This is kind of what a northocite looks like. It's got quite a lot of very what are called felsic minerals. So feldspar is the main mineral component of a northocite, and it's shocking it over and over again by repeated impact events. Plus, it's very light toned. It's already a light toned composition. It gives it this kind of whitish, almost bluish color in places. And so one of the reasons why we're going to Kamastastin is because it's got the right composition, the right rock type. The other is that it's an impact structure. And so with it being an impact structure in the right type of rock, it makes for an ideal test bed for training programs for astronauts that are going to the moon to then look at these types of geological structures in the same type of rock that they would see on the lunar surface. And to kind of point out loosely what we're seeing here on the right of the slide is Tycho crater on the moon, where we see that kind of terraced outer rim and the central uplift. And though we can't quite see the terraces here on at Kamastaston Lake on the left, we do see this island in the middle of the lake, and that is essentially, well, that is the impact structure central uplift. So very similar to what we'd see, what we're seeing on Tycho on the moon. And just to show you what that looks like from a more orthogonal view, we took this while during some of our traverses. We can see this white toned rock here. That's the anorthosite. And this island in the center of the lake, and also to give you a sense of scale, is the central peak for this impact structure. And so we ventured out there with this fantastic group of people, a mixture of folks from the University of Western Ontario, and folks from NASA Johnson, so people who are responsible for the flight controllers, people who are responsible for telling astronauts what to do and when to do it. And of course, we have a few of the astronauts themselves. This is Rajachari, who has already flown in space. This is Christina Cook, one of the Artemis II astronauts. Jeremy Hansen, also, this is our Canadian Artemis II astronaut, and Jenny Gibbons, who will be Jeremy Hansen's backup, as recently announced by the Canadian Space Agency. We also had the support of the Innu Nation. They were the guardians of the land and were there to ensure that the land was treated fairly. But they were also there to make sure that everybody was safe and okay. And they were there providing just a lot of support and sharing their stories and teaching us about their culture and about the history of the land from their perspective. And we were there to teach them what we could about what we knew about the land as well. And in this was a lot of good good-hearted exchange, and they brought us far more char than we could eat. So we ate fish that they caught for us for days, which was a really fantastic way to spend our time there. And so, how did we get there? And the way that the way this worked was we had to get. I don't know if you can hear that. It's kind of loud for me, but anyways. The way this worked was we flew in on these incredible planes called Twin Otters, which can stop on a dime and take off from a runway that's almost maybe barely over a football field in its length. And they're used for sometimes for going to really remote places, like even more remote than Mustaston Lake, places like Antarctica, where it used to be used to land on the ice and you drive a snowmobile up into the back of it. So it's a really incredible vehicle, and it's really cool to have used it to come out here. And we took 3 or 4 flights to get all of our gear up there and all the people. And when we did, we got ourselves set up with camp, and so we lived at these sites for about 2 weeks near the First Nations huts that were already there. And the way this camp was set up, we had 3 different points. We had our kind of sleeping quarters where all the individual tents were set up. We had our communal tents where we did our planning, and we sorted all of our gear and cooked all of our meals. And then we had the toilet tents where we did that stuff. Anyways, in the main tents, we'd organize what we're going to be doing for the day. This is our fearless leader, Dr. Gordon Ozinski, and he was there to provide an overview of lessons that we were going to be doing each day, and would point out much of the same stuff that I pointed out to you earlier in this talk. The similarities that we see between the impact structures on the moon and Kamastaston Lake, and what that means for what we're looking for, and the type of structures that we see around the impact structure, and how to recognize where we are within an impact structure when it's not necessarily immediately obvious. And this, as you can imagine, is a very large impact structure. And so getting around involved hiking to a lot of these places. We got around on foot for most of it, and we'd have to pick one site that we were going to per day for the most part, because everything was so far away. When we could, we hiked there, but more often than not, we'd have to take the boat out across the lake and go to places that have been explored by other expeditions out to this site. And we'll focus in on that feature that's in the background. As I mentioned, these are very melt-rich environments in the aftermath of impact events. And so when that melt solidifies and cools, it creates this really competent and strong, sturdy rock. One thing that's different about impact structures on Earth is that we have things like glacial erosion. And so that's what happened here. So the vast majority, well, I said the majority, but quite a bit of the rock that would have been sitting around this big, darker structure here was eroded away by glaciers. But because the melt that makes up this rock was so sturdy, it kind of created an obstacle that the glacier had to then move around. And so the glacier eroded everything else that was around it. And in sort of the pressure shadow of this more sturdy pool of melt, it deposited a lot of the sediment the glacier was already carrying, creating kind of like this this pointed, elongated feature as a tail behind the initial obstacle of melt. This is called the Roche-Montagne. It's a glacial feature that tells us about the direction the glacier was going. So you can see, based on the direction the tail is going, that the glacier was going towards the left of this image. But importantly for us and relevant to our exploration, it highlighted a melt pond that we would then be able to go and look at in detail. And so that is what we're doing here. So we're actually right up against that outcrop, looking at the melt that we see. This is Gordon Zinski showing Jeremy Hansen and Jenny Gibbons the kind of textures that we'd see in the rock and what indicates that it's melt. And what would indicate otherwise. And so this is important for the moon because impact melt is a type of rock that's created by melting the layers that already exist. And so by taking all that material, melting it and homogenizing it, we get kind of this natural geochemical homogenization of this material, and it tells us a bit more about what the lunar's interior might be like, especially in the case of massive impact events where you sample very deep beneath the crust and you're bringing up material that might not even have been fully solid. So that is a theory for some of the impact structures on the moon, is that they were such massive impact events that they sampled beneath the crustal exterior of the lunar surface. And so if you have a melt pool that exists from that material, that tells us about the internal structures of the moon. Focusing a bit more on the melt rocks, one way that we were taught to recognize them is that they tend to have these columnar structures. You can kind of see it here on the right of this image, kind of like the columnar jointing. You'd see it the Giant's Causeway in Scotland. You can kind of make it out here, where we see these columnar joints that propagate vertically throughout this outcrop of melt. And so looking for features like that on the lunar surface would tell us more about how we could potentially prioritize targets if we're looking at exploring the hows and whys of the moon's formation. Another thing we want to focus on is impact breccias. So a breccia is basically a rock that is made up of lots of other smaller pieces of rock. So you imagine in an impact event, you're shattering the target rock and bits of it are flying everywhere. But in some cases, these bits can are reassembled together, not perfectly, but by this matrix that that sticks them together and exists between them. And so what we're seeing here is this is Jenny Gibbons looking at geological contact between a melt rock here over top, and then you can kind of make out the clasts that are in this breccia here beneath it. And so this contact, rather the breccia itself, tells us a bit about the target material more directly, and can tell us about what it sampled if the target rock was layered, had different geological layers. Those layers, the types of rocks that are in those layers would be preserved in this breccia. Another thing that we want to look at is the target rock itself when it has not been impacted. So that's another thing that's important to teach our astronauts, as they go and explore, well, in preparation for exploring the lunar surface, is how to recognize something that might not be an impactite, something that might be primary and unaltered by an impact event. So this is important because it could indicate something like young volcanism on the lunar surface, well, relatively young. And that would tell us a bit more about lunar's volcanic processes, which is not very well understood to this day. And of course, we teach them how to use our sophisticated instrumentation, which often involved in this case just hammering away at the outcrop. But we also have much more sophisticated instrumentation. So using handheld analytical instruments like a laser-induced breakdown spectrometer, which is really quite popular on the rovers these days. So it's used a lot on Curiosity and Perseverance on Mars, essentially firing a laser at a rock, ablating a small bit of it, and then using the color of the plasma that the rock is converted to tell us what the composition of that rock actually is. That said, astronauts using those types of tools on the moon might be fairly far out. And so we focus on kind of the fundamentals now, which is, can you break it and look at a fresh surface? Because when we're seeing rocks just on the surface of the Earth, they have a lot of weathering that's caused by interactions with water in the atmosphere and, well, in this case, the lake. And so if you break it open, you see a face that has not been altered by the atmosphere. And so you can see what the textures are more likely to be like if you witness them on the moon. And in the midst of all this, we did have some downtime where we could meet in our tents at the end of the day, wind down, talk about the day's events, and plan out what we could be doing the day after. And of course, there was great company and amongst ourselves and all the biting insects that we kind of wish weren't there, to be honest. But even in the wake of that, it was still a fantastic trip, and it was great to see all these people in action. These really incredible group from Johnson and of course the astronauts. And with that, we are kind of looking forward to what's next, and that means we're looking at exploring the lunar South Pole with rovers. So Canada is launching its first ever more or less independent rover mission. My role in that is I'm mapping some of the landing sites of the South Pole, which do overlap with the potential exploration sites for Artemis 3, where we are going to be sending astronauts on foot. And so we're hoping to do some kind of exploratory work with that. But further down the road, there's also Lunar Gateway to look forward to, which is essentially another spiritual successor, this time to the International Space Station, that will go and orbit the moon and allow astronauts relatively easy access to the lunar surface to and from that space station, where we can then conduct more operations. And so with that, I just would like to say thank you very much for listening. And I hope the astronauts come back to these amazing sites as they get to see things they've never seen before, like the Northern Lights from below, which is something I never thought I'd ever hear anybody say. So thank you very much for listening. I hope I was able to tell you something you didn't already know. And with that, I guess I'll turn it back to you all. So thank you very much.
Thank you. All right, a few questions for Dr. Svensson? Yeah. I might have to repeat that.
Oh, no, it's okay.
Okay.
So the question, I believe, was, are the terraces in the crater still visible from under the lake? Can I just get a yes or no as to whether or not I heard that correctly?
You heard it correctly. Yes.
Okay, great. Okay. And that's something that I'm actually quite keen in exploring. The problem is that because of the glacial erosion, you're depositing a lot of sediment into the water column, which would then cover up those terraces and make it difficult to see just by looking at it. I've recently gained a new obsession in scuba diving, and so I've heard that others have dove in this lake, and I'm kind of keen to dive it and explore the structures that exist beneath the surface of the water. But there's still the issue of the sediment that likely covers these terraces and obstructs our view of the outcrop. And so something we can do to address that potentially is to use ground penetrating radar from the surface. And so we can maybe see if there's an association with the radar maps that can highlight where these terraces may or may not be beneath the surface of our sedimentary overlay. And that won't penetrate through water, but it can penetrate around. It can penetrate through the loose sediments on the surface around the banks of the lake. So I guess they're likely still there. although a large volume of it's likely been eroded by glaciation. That said, you can still see some of the tectonic structures that existed. So the answer to your question is yes and no. It's there, but they're tough to see. I heard when this impact, when did this impact occur and how? I didn't catch the other part of that question. I'm sorry.
And how do you determine when it happened?
Okay, great. This is a great question. So this impact is about 36 million years old. And the way you determine that is by studying minerals that formed at the same time as the impact event. And so the best way to do that is to look at rocks that formed at the same time as the impact event. So you can do uranium lead dating on minerals that formed simultaneously with the impact event in the rocks that formed simultaneously with the impact event. And those rocks are the melt rocks. And that's another big reason that I forgot to mention. So thank you for bringing this up, is to why these melt rocks are so important, why we're so keenly interested in them, is that they represent the conditions of the impact structure when it was formed. And so this is really important because I mentioned the late heavy bombardment earlier. We have one Apollo sample that we were able to date and say, okay, this pool of melt from this one impact structure occurred this many years ago, and we can see that this impact structure has been overprinted by this impact structure, but it also itself overprints another impact structure. And so by this sort of law of superposition, you extrapolate from this one data point the relative age of several hundred other impact structures. And so that's why it's very important to get samples from other melt sheets. We can then have another number to use to actually gauge how old some of these impact structures are, because right now, the timing of that late heavy bombardment is based on one data point. And so if we can have, two, that at least that'd be pretty great, right? So yeah, so essentially you use different isotope dating systems to understand how old the minerals are in these rocks that were formed concurrently with the impact event, and that tells you about the history of the region and the history of the lunar surface. I got how high was the cliff that we were in, and what else? Sorry.
The one that blocked the glacier, how high was it and how much of its height did it lose?
Oh, that's a good question. We actually do think it lost a bit of its height, but we can't quite say for certain. Its height was about 70 feet. So it was this fairly, I mean, from our perspective, massive pool of rock, and that's not even the deepest section of melt. So the deepest pool of melt would actually be beneath the lake, because melt tends to pool within, the topographic low, which is going to actually be within the basin, but it does pool outside the bounds of some of the impact structure itself. And so, sorry, the other question being how much it would have lost. Yeah, we're not certain how much it would have lost, but we can study how it changes vertically. And so we can use what we know about melt sheets that are formed by impact events to say, okay, we know that they should have about this much of features, structures that look kind of like that look one way, and then this, this much of structure that should look another way beneath it. And if it's missing a certain amount of that of one structure, then maybe that was all maybe all that has been eroded. And so it's not a good estimate. And so that's why I say we don't really know, because we don't actually have a good understanding of how these melt sheets change vertically. But our best guess is probably like a few tens of feet, perhaps, over top of the melt sheet that may have been lost. But in terms of the whole area, I know you didn't necessarily ask about this, but it's still important to answer your question. The whole area experienced different degrees of erosion from glaciation. And that's for a number of reasons: accumulation of melt in some areas, and exposure to glacial erosion unprotected from melt in other areas. So you had some areas where you lost only 20 feet, and other areas where you may have lost like 70 plus feet. In this particular site, we think we may have only lost 20 feet over the melt sheet itself. Yeah, I mean, you're more or less exactly on the nose there. So, in the astronaut corps, they tend to contribute to uh, astronaut activities, so active duty astronauts in other ways. So, for example, if you have astronauts doing a spacewalk on the ISS, you usually have another astronaut in flight control, giving them instructions alongside the flight controllers, so they can see what's actually going on and they get a sense of what's happening. And it builds a sense of community and team building amongst the astronauts. So, in this particular case, we have astronauts that are potentially doing the exploratory work that will then create the foundation for a training program for astronauts that are going to be going to the moon. So, yeah, while the astronauts that were out on this expedition may never actually stand on the lunar surface, there's a good chance that their feedback and their experiences here will guide how people create training programs at this site in the future, and how astronauts that do go to the moon are trained at this site. And I should point out, this is something that I apologize, I didn't do a very good job of pointing out in the talk, but this is a very, very special site, Kamastassin Lake. There are only a handful of places on Earth where a north of the site outcrops. And for a site, for a rock type like northsite to then also be hit by this this random projectile from outer space, it's like 1,000,000 to 1 odds. And we actually have 2 sites like that in Canada. Manicouagan Lake, also known as the Eye of Quebec, is an impact structure that hosts a northsite, although it isn't exposed well. So Kamastassin Lake has likely the best exposure of a northsite in an impact structure in the whole across the whole world. And so this is really a world-class site for training astronauts. And so it's really important that we have a good understanding of how to use it to train these astronauts, and that's why astronauts that aren't necessarily going to be on the moon are here and are developing training programs that will then be used to help train the next generations of astronauts that go walk on the lunar surface. Sorry, a schedule for the Artemis program for developing more training. Sorry, I don't think I quite understand the question.
For training.
I don't know for certain. I have heard from Jeremy Hansen, at least Jeremy Hansen believes that it is 100% likely that this site will be revisited by NASA astronauts and Canadian astronauts. Well, I mean, of course, Canadian astronauts, but it is very, very likely that this site will be used for astronaut training again, because it is such a rare place and such a world-class site for studying impact cratering in a moon-analogous material. Sorry, I didn't hear that. Could you please repeat the question?
Where did the otters land at the crater site, and where were they ferrying equipment from? So where were they flying from?
Oh, yeah, fantastic question. Actually, I can just go back to the map and show you. Just quickly go back here. Oh, maybe it's further back than I thought it was. Okay. All right, assuming you can see my little laser pointer, this little kind of beach here is where we were camped, right there, that kind of elongated spit that's outlined by this river here. So we were camped there, and the Twin Otter lands coming from the south, right around there. We flew out of Goose Bay, which is a small town in Labrador that was formerly just a military town during the Cold War. Something that's kind of cool, fun fact about Goose Bay: the Avro Vulcan, which is Canada's, I think, only nuclear bomber, now decommissioned, is sitting as a decorative piece outside Goose Bay's airport. And so you walk by this old Titan as you get on a Twin Otter and fly north to go to this really remote site. Another thing that I'll say about the Twin Otters and flying to places like this is that there's no flight tower, there's no flight control tower there. And so you really have to rely very heavily on weather predictions. And so when you're landing here, you've got nobody guiding you down. And so with the high topography, because of this kind of mountainous terrain that's created by glaciation, all these valleys and hills, if you don't know where you're going, you could crash pretty easily. And so if it's too cloudy, you just don't go. So you have to, or you turn around, really is what's more likely than not to happen if you're the first ones out there. So you have to be very careful to communicate back and forth using like an Iridium satellite radio or another device like that. what the weather conditions are like. And so the Twin Otters just kind of land by sight, which to me is incredible and just absolutely unheard of. But
Mhm.
when you go to remote places like this, that's kind of common practice.
Matthew, I'm curious, when you were talking to the members of the Innu Nation and telling them that two of the people in your group were going to be flying to the moon next year, what was their reaction?
They had a story, very serendipitous. So in the Innu Nation, in their community, they had a story about a member of their community who brought down, I think, a piece of the moon to this place, and that's why it was so sacred in their stories, was that it has like this kind of heritage connection with the moon, and some of their beliefs about this place are already connected to the moon. And so when they learned that we were going to the moon because of what we found here, they immediately kind of were like, "Wow, that's incredible! We have this story about how we believe this place is already connected to the moon," and it was really cool to hear that and to see that very 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 cool cultural connection between science and legend and stories.
Okay, well, Dr. Svensson, on behalf of the Mississauga Center, I'd like to thank you very much for a very interesting talk. Thank you.
Thank you. I do apologize I couldn't be there in person. I'm a new uncle, and I am now responsible for taking care of a brand new baby nephew. So I regretfully can't be there, but thank you for listening to me all the same.